Hey, all my JavaScript friends, this is the Virtuoid, aka Mike Smith, and this is Fun with JavaScript, our model racing game. If you like this video, please click on the like button below, subscribe to this channel, or leave a comment. I'd love to hear from you. The first thing we're going to need to do is we're going to need to make sure that our physics are correct. Now, I can sit there and work on the model cars or the model track, but the fact of the matter is if they don't work together, this is worthless. So I want to make sure that we can get an object created that will be affected by gravity and that when it hits something, let's say the ground, then it will react with it. So some sort of physics, some sort of gravity, some sort of collision detection. And so that's what we're going to work on today is we're going to get the bare minimum coding that we're going to need to be able to get our models, some model working with some sort of ground and be able to show that, yes, we can introduce gravity into our project. So let's first get the preliminaries out of the way. We have to initialize our repository. I have a complete clean repository here. Absolutely nothing's been done to it except for the creation on GitHub. So let's go through all these names. Okay, we're done with that. And we just did an npm init. There's really nothing about, nothing really spectacular about it. So we have our package.json file, and there is what it looks like. Not a big deal there. All right, so the next thing we're going to need to do is let's install all of the packages we're going to need for our race game. This will include the development packages and the dev development packages. First thing we're going to install is Vite, which is our package manager. You can also use Webpack if you wish. I just prefer to use Vite because I like Vue. Our next thing to install is the post-CSS nesting, and this allows me to be able to use the up-and-coming post-CSS syntax in my CSS files. If you're used to Sass, it's kind of like Sass, but it's a little bit, it's not quite as complicated as Sass, and it will be part of the CSS specifications at some point in time. And that completes our dev dependencies. You can see they've now been added. Okay, don't ask about that again, don't ask about that again. And that's just my IDE doing that. So we got our dev dependencies here, our post-CSS nesting, and our Vite. Now what we want to do is let's go ahead and install our dependencies. Now if you watched our introduction video, I told you that we are going to need to install BabylonJS, and we're going to need to install our Ammo.js. Our Ammo.js is our physics that interacts with BabylonJS to give us all the cool stuff. Of course, Babylon is our 3D graphics engine. So let's get started on that. First of all, to install BabylonJS, there's actually a number of different modules that you need to install. And they are listed here on the browser page for BabylonJS. This is all the available packages. We're not going to use all of these packages. Basically, we're going to need the core, which is the Babylon's core. We're going to need the materials, which gives us all of the routines for creating the spheres and the models and all that kind of fun stuff. And the loaders, which will allow me to load in external models. So if I ever build something from Blender, or if I find something in open source that gives me a really cool looking car or a tree or a house or something like that, that will allow us to add it in. Post-processing, textual serializers, GUI, and Spectral, all that kind of stuff. We don't really need that at this point. We may need it later, and if we do, we'll install it later. So let's get those three installed. There's the core, then the loaders, then the materials. Really easy and quick. So last thing we need to install is our Ammo.js file. And there that is. Let's get that installed. And that has now been installed. So let's take a look at our package.json file. And it has now changed. There's our dev dependencies. And here are now our regular dependencies, including the three BabylonJS libraries we're going to need, plus the Ammo.js. All right, last thing we're going to need to do here for our initialization, well, actually not last thing. Last thing is that package.json, so we need to get our scripts put in there. And these are the scripts that Vite is going to use to be able to do its fun stuff. And it's real simple here. This is the dev. We're going to use that one to do the hot loading dev environment. And the build and the preview is what the preview is when it's going to build it, but it still puts it on our local server. Build is when we're going to actually build a distribution for eventually put on a website. And we're not going to get to that for quite some time here. But this should complete everything that we need on our package.json. Now, a couple of other things files we're going to need here is that we're going to need a file to configure our Vite and to let our Vite know exactly what it needs to do. So I'm going to copy that over from my test bed that I've been working on. Okay, and here's our vite.config.js file. And this is very simple. There's really not a whole lot here. The big thing here is I want to make sure my server is port number 3000. With Vite version 3, they changed the default port, and everything I'm used to is port 3000. And this just basically says we're going to use an index.html file. No biggie here. The only thing that we do want to add in here is that we want to add in our post CSS configuration. Vite will automatically pick up a post CSS configuration for us. Without it, we wouldn't be able to use post CSS, although we installed it. And that's all there really is to that one. I mean, it's not a big deal on there. The one thing I do want to mention here is that notice this is a .cjs file, and we're doing that because we got to be able to differentiate within Node whether we have a common JS file, which is what this is, or just a regular JavaScript file, which is what the vite.config.js is. So technically that should get us up and running, but let's add just enough to be able to make sure that our server is indeed working. So what I'm going to do is I'm going to add in a new directory called source. This is where everything's going to add in. There's my source directory, and the only thing I want to add in here is going to be an index.html. And there's the default .html file. So since our vite.config is saying I need inside the source directory, we're going to put index.html. We're going to put our HTML code there within the HTML file. And we'll use that to make sure everything works. Okay. All right, so this is our index.html file. No big deal here. The real key here is I've got a JavaScript fwjs race.js file. I'm not going to worry about that right now. I'm not going to worry about the icon, which means we'll get 404 errors, but I don't care about that. I just want to make sure that our server is running. So let's bring up our command prompt, and to run our server, all we have to do is say npm run dev. All right, it's saying that localhost 3000 is available, so let's bring up localhost 3000. Ta-da! Okay, so that means that our HTML server, development server, is actually working. Obviously, nothing's there because I've got no code. I just got the simple HTML file. We got the 404 errors for the icon, and for the JavaScript file, I don't care about that. So that covers everything we need to get everything on initialized for our development server. So let's get to the actual development. What is it that we want to accomplish? We want to be able to get some sort of model, car model, I don't care, any kind of model, to be able to interact with the ground so that when it hits the ground, it will basically know that, hey, I can't go any further. Although gravity is pulling me down, I'm not able to go any further than where the ground is, which of course makes sense. The ground kind of represents the track. We also want to be able to say, okay, if this track is tilted in some way, I want to see whatever that object is to be able to follow the contours of that track. And that will prove to us that both gravity is working and that we've got collision detection working between the model and the track. Luckily for us, BabylonJS has some great examples out there. And the one that comes closest to what we're going to want to do is found right here. So here we are. We've got a skull, which represents a model, and it's sitting there on top of a ground, or a plane in this particular case. So what does this prove? Well, watch when I hit the play button. Watch what happens. Boing. And it fell over. In this case, it fell over. But notice it started at the top, moved down, and once it hit the ground, it stopped, bounced a little bit actually, and then it kind of fell over. I hit it again. You can see it again. Oop, fell over. Notice it also fell over a different way, which means it's not consistent each and every single time, which is very good for us. That time it just stayed straight. So that's the idea here, is that we want to be able to simulate that. And luckily they've given us all of our code. Now, the biggest problem we're going to have here is that this particular code, first of all, is using vars. We're modern JavaScripters. We don't use vars anymore. So we're going to need to be able to convert this over to use the more modern JavaScript. And also, I just happen to know that this is also loading in everything as if as if you have script tags within your HTML. So what you'll end up with is you'll have Babylon here as a global variable. And we don't want that. We want we want ES6 with tree shaking. And Vite will give us all that. So we're going to need to take all of this code here and convert that over into our JavaScript file to use ES6. Real simple. So let's get to our code. Let's get it situated correctly here. Within source, we're going to create a new directory. And that new directory is going to be called CSS. That's going to contain our CSS code. Let's go ahead and create our CSS file. Our style sheet is going to be post CSS, and we're going to name it fwjs.race. And there's our post CSS file, no big deal there. We're going to create a directory called JavaScript or JS. This is where all of our JavaScript is going to be in, and that one JavaScript file is going to be fwjs.race. There's our JavaScript file. And then finally, we're going to have a models file directory. That's where we're going to contain all of our different models, in which we'll eventually put that little skull model in eventually. So we've gotten our code situated there. So let's open up our JavaScript file. Let's go into our playground, and let's copy all of this code. Let's go back into our JavaScript file. Let's copy the code. And let's go ahead and start making the changes. And I'm not going to sit here and make all these changes and just get you suffering watching me make all these changes. So we'll come back to once I'm done, and then we'll start getting everything all fixed up. Okay, and we're all done. And so what exactly did I change? Well, basically, one of the things I did do is that if we go back to our code here, it creates the scene. But there's a lot more to doing BabylonJS than just creating a scene. You also have to create an engine, and then you have to run the simulation. And that's what's missing from that other code there. So from this point on, all that code is exactly the same, except that I have changed things like, things like, from a var to a constant, basically. Other than that, everything else is exactly the same. A couple of things I do want to show you, though, if you are going to start working some of the examples in BabylonJS, is that when you create things with the create ground or the create sphere or the create box, we don't use mesh, we use mesh builder. Let's go back to that code and show you some very important thing that you need to take a look at. For instance, a good one here is to create the ground collider. So we do var ground babylon.mesh.create ground 662 scene. Well, everything here within the version that you get static wise is passed one little piece at a time, but that's not true when you're passing it through ES6. It's going to be the name, your options, and then a scene. So everything's got to be converted with an option. So I had to do some extra work, look at the API to make absolutely certain that instead of saying 662, I just say 66. The 2 is the number of divisions. I don't worry about that at this particular point in time, so I just got rid of it. Other than that, all this code is exactly the same. So let's go through real quickly what this code looks like. Actually, let's do this. Let's do this first. Let's go ahead and save it. And let's go into our Fun with JavaScript and make absolutely certain that it works. And boom, failed to resolve import Ammo.js. I forgot to bring my ammo file over. And let me tell you why that was important. All right, so we have a problem with using the Ammo.js file with the Vite compiler. And the problem is that the Vite compiler is having problems converting the CommonJS code that is within the Ammo.js and using it within our ES6 arena that we're building here. And that can create all sorts of problems. So for instance, let's take a look at the code that I've got here. I'm going to do this. This import ammo from Ammo.js is basically now getting the import from the Ammo.js that we installed a little bit earlier. So let's take a look and bring it in from that. And let's save this off. let's run the code and see what happens. All right, we run the code. Still absolutely nothing has happened. Let's do an F12 and let's see what kind of error that is giving us. Uncalled error, cannot set properties of undefined setting ammo. And the problem here is that within the Ammo.js file is doing some sort of funky stuff where it just doesn't work very well with ES6. And Vite, for some reason, cannot figure that part out, and it just kind of just bombs on us. So I had to do something to get this thing to work that you should never, ever, ever have to do. Don't ever, ever, ever do what I've done. I've created my own Ammo.js file. So let's go ahead and let's move that file over, and I'll show you what change I've made. So I've got, let's move that over. It's at 1.9 megabytes in size. I mean, seriously. This Ammo.js is really powerful for what it does, but to be honest with you, it is really, really huge and massive. If I can get Canon to work, I'd use the Canon JavaScript JavaScript physics file, but I can't, so that's the way it is. I can tell here it's gigantic, it's ginormous. Down at the very bottom, though, I did make a change. This .ammo.equals_b was what was originally there, but that's incorrect. What happens is that this is not defined, or Vite does not have a definition for this. It assumes this is window, actually. So all I did was I took that part off, and then I just said export default ammo, because ammo is already being loaded up into the namespace for this file. By doing this, I've created it into an ES6. But the issue is here, I have modified the library. You do not ever, ever want to do this. And I promise you, probably within the next week or so, I'm going to put some headphones on, get us some great music, and I'm going to really dive into Vite and roll up and this ammo package. I'm going to figure out what configuration I'm going to have to set up inside of my vite.config.js to be able to get it to work with the distribution part of ammo, so I don't have to do what I've done here. But here's the thing. I wanted to get this video out. We need to get this video out. I need to keep working on the tracks, and need to working on the models and make sure everything is working. So I've went ahead and did this for right now, but I'm ashamed of myself. I'm embarrassed. But sometimes you got to do what you got to do to get things to work for now. But I promise you, hopefully the next week or two, we'll get the whole thing figured out. So I've now got that changed up. Last thing I do want to do is I want you to notice at the very top, I have FWJS and import styles from CSS FWJS race.pcss. And this is how Vite embeds the CSS within your JavaScript file. So this basically delivers CSS via JS, and this is done this way so it can reduce the number of resources that it goes and gets. So last thing I want to do here is let's change our what's it called? Style sheet. Yeah, let's change our style sheet. I've put the background color to black and the color to aquamarine, and I've set the size of the world. The world happens to be my canvas right there. So that should fix our style sheets. So that will then import it inside here. So let's just see if everything works first. And there it is. Where's the skull? Well, because it already rebooted itself. I did want to take one thing off here because I don't want to do this yet. I just happened to notice that. Let's save that. Go back into here. Let's do a Control F5. And where's the skull? Well, because we haven't brought the skull in yet to the models. So last thing we want to do is let's bring the skull into the models. Da-da-da. So I just took this straight off of the Babylon website. I don't care about opening it. Don't care about registering it or opening it up. So there it is. There's my skull.babylon file. And again, I'll explain all this through the code here very shortly. Let's do the Fun with JavaScript. Let's do a Control F5. And there we are. Ta-da! Do a Control F5. Works like a champ. Let's see if it ever falls over like it does. Yep. Ah, there it goes. There it falls over a little bit. So we now know that the gravity works. We now know that it works with the model and it works with the ground there. Let's go ahead and do a quick rotation on the ground. and see what happens. There it goes. So now we know that gravity works well enough that when we rotate the ground to make sure that it looks like a, that it has some sort of slope to it, that the models will actually work with that slope and do whatever it has to do. And oh man, okay, it's barely sliding down now. Oh, look at that. Oh, that's terrible. Anyway, actually that's good. That's kind of what we want. There's a lot of different things that we can set on this, on the ground and on the model that we can help control how all that works. So let's take a look at the code itself and break it down and show you exactly what is happening. The code behind it. Let's take it one little step at a time. I'm not going to worry about, obviously we got the imports. We know about that. All right, the Ammo.js, we've already talked about that, how stupid the stupid thing that I did to be able to get Ammo.js working. There is one additional command that you have to load up. You have to, and that's with the await, to be able to initialize Ammo, and that's that little delay that you see within the code. Let me just bring that back up again. If we hit F5, you can see a quick little delay. That is the F5. That's the, it's not the F5. That's the code that initializes the Ammo library. So we got that done. All right. The very first thing here within the system is I've got to create a new engine, and this is not what's part of the code here. Let's bring back the playground code. Here's the original playground code. Notice it starts with the create scene and it does a return scene because they have within their playground encapsulated or they have the engine part that is completely outside of the realm of the code. You're just working with the scene itself. So in our particular case, we have to create the engine, and the engine is what runs the entire process. Scene. What is a scene? A scene is merely what you're looking at. If you think of a stage play, a scene is the stage. It has all of the camera angles, it has all the lighting, it has what the actors are on, it has what's happening on the screen, what happens with the actors, it has all the paraphernalia on the stage. So basically a scene is the stage. So you've got to create a new scene and pass to it the engine, and that will give you the ability to say, okay, here's your stage. So next thing you want to do is, what are we going to do with the stage? Well, we're going to add a couple of things. First of all, we're going to add a camera, and there's a bunch of different cameras that you can have available. One of the cameras that I know we're going to be using eventually would be the camera that will follow the leader. If we have a 4-car race and they're racing, we're going to want to try to follow the leader. So I'm going to have one car that's going to kind of sit behind the leader at all times and just kind of follow them down the track. We may also have a bunch of different cameras to show different angles at different important points of the racetrack eventually. For now, we just want one simple camera. And basically the idea here is we give it a name, and then we tell it what position it's going to be at. Now, everything here within, I'll just use this screen right here, but everything that you see here is a 3D screen that has been implanted, or a 3D view that has been implanted on a 2D screen. So you have to kind of conceptualize. In this particular case, we have 3 numbers that we're going to be passing to this vector 3. And this vector 3 basically defines an X value, a Y value, and a Z value. The X value in this particular angle that we're looking at now, and of course it changes based upon, where you're looking at, but at this particular angle, the X value is running from left to right. Basically, from the left-hand side of the screen to the right-hand side of the screen. That's going to be the X axis. The Y-axis is running from the top of the screen to the bottom of the screen. Now this is basically the same as if you were looking at this as a piece of graph paper. The X is always the horizontal line and the Y is the vertical line. So as we're looking at this thing, the Y-axis is up and down. The Z-axis is the third dimension, and that basically represents what is closest to you to what is furthest away. So as we're looking at this longer line that we see at the bottom of this ground here is the beginning of the Z-axis, and as we move toward the back line here, that is the ending of the Z-axis. So as if we were making this thing larger and larger, the back or the other part of that Z-axis will get smaller and smaller and smaller until it completely disappears. That's your perspective. So X-axis is left to right, Y-axis is up and down, the Z-axis in this particular case at this viewing angle is our perspective angle, what is closest to us to what is furthest away. So when we give it a vector 3 here, we're going to say, okay, I want the x0, which is going to be position number 0, right smack dab in the middle. I want y5, which is going to be 5 points up the axis, and -7, which is going to be 7 points toward me. So with this free camera here, we've got the z-axis is in the middle. The y-axis is going to be a little higher. So if we also had y as 0, then this would be basically right at our face. And the z is going to be -7, so we kind of backed our way up a little bit to kind of get a better view of the camera. So let's just play with that number real quick to see what happens. So that was z of 7, -7. Let's double it. Let's do 14. Let's save that. And if we go into our Fun with JavaScript, notice how much further back we are. So if we put z of 0, now we're at the very top. So as you can tell here, as the z, with the z itself, you know, we've got further away. Now that we got 0, we're pretty much right on top of it and looking over it. Now, why are we not looking back toward the distance like we were before? Well, that's for another, we'll explain that in just a second. So let's put this back to -7 like it was before. And let's just play with this y-axis. So y was 5. Let's go to 0, and let's see what that does. And now we're looking at it straight on, and it's a plane, so it looks like it's kind of floating in midair. It's really not. Let's just hit F5 again. And there it's sliding off. Let's see if I can get a better slide. Yeah, there we go. So the poor thing looks like it's now kind of floating in air. It's not. It's just that with the y-axis, we are at the very level of the plane. So if we put -5 there, we should be below it, right? Let's hit F5 again. Yeah, we're kind of below it. Why can't we see it? Because we declared it as a ground. You can't see the bottom of the ground. You can only see the top of a ground. That's the reason you can't see it. Just a little thing there. So that's what the y-axis there for 5 looks like. Now we're back to, I'm sorry, the y-axis would look like. So now we're back above the ground. Let's do the x. So that should bring us left and right. So let's put 10 in as x. That moved us to the left a little bit. But notice it didn't shift us to the left. We're still viewing it as if we're still looking at the plane itself. And I'll explain that in a second. So -10 should bring it to the left-hand side. And it does. So let's put it back to 0. So I kept saying, you know, that, well, you know, it didn't shift over. It kept looking at the middle of the plane or the ground. And why is that? Well, that is because of the very next command, set target vector 3 0. This vector 3 0 is a special function that says I want you to return a true 0, x of 0, y of 0, z of 0. I could have said new vector 3 0 0 0 here. So no matter which way I move my camera, it's always going to be looking towards the center of the screen, or the center of the ground. In this case, it's 0 0 0. No matter what. So that's the reason that, you know, when we did the X, it didn't shift everything over and just put it to the left. It moved us, but then turned the camera over to point back toward the middle. And then, of course, we're attaching the camera to the canvas itself, which is our HTML canvas that we've defined at the top here. So that basically takes everything for the camera. All the cameras work pretty much the exact same way. They just behave differently once you're starting to interact with them. And we won't get into that with this video. We'll get into that later. Light. All the lights work the same way. This is a hemispheric light, which lights up the whole hemisphere. Again, it has a vector. And this vector basically says, where is this light located itself? And so the nexus of this light, or the light source, is located at x0, z of 0, and y of 1. So right straight, just a little bit above the ground itself. What happens when we put it below the ground? Let's say -1. Well, let's find out. The light is now below the ground, so of course the light has not lit up the ground itself. And since it is hemispheric light, we got a little bit of light bleed floating around, so that's the reason we can still see the skull, but of course we can't see the ground because it's not lit up. How intense we want the light? Well, we want it 0.7. The intensity, I believe, goes from 0 to 1, so this is a pretty intense little light. If we were to set this to 1, let's see what kind of changes that makes. Yeah, that's a very bright light, much brighter than it was before. Well, how about a 0.1? 10th intensity. Now you can barely see it. So the intensity controls obviously how intense the light is. So let's put it back to 0.7 like we had it before. All right, now we're getting to the fun stuff. Enable physics. All right, so when we enable the physics, this is very, very basic. It takes two arguments. The first argument is the gravity vector. If you specify this as null or undefined, it will use the default gravity vector, which is 0, 9.81 something or the other. Whatever the gravitational constant is in physics, that's the number that it uses. And it makes it negative because we want it to fall negative with the y value, so it falls down. And of course, a z, we don't want it to go anywhere else, which of course means if you want some weird gravity, you could, let's say, have an x of 10 and a y of negative 10. So it will not only will it slide down, but it will slide off to the right. So you can do some really funky little things with that. We're not going to do that. We're just going to make it straight, plain old gravity. And then we're just going to tell it, hey, we want to use the Ammo.js plugin. And here is our Ammo. This is our Ammo object that we created way back up here in line number 14. No biggie there, but that enables the physics itself. And that's where we're going to start working with physics imposters and things like that. And we'll explain that here next. Next, we're going to create our ground. And that's with the mesh builder create ground. And we'll give it a width and a height. The big deal there. This is where I rotate the ground. And rotation is done in radians. I would suggest Googling it up. I had to relearn all that. I learned all that kind of stuff back, in high school and completely forgot all about it. Of course, because high school was like 150 years ago. But it's in radians, so this math.pi divided by 32 gave me exactly what I needed. I'm not worried about that. What I want to explain here is this next line. Ground.physicsImposter. Okay, so let's talk about physics imposters. This is back to the BabylonJS code, and basically a physics imposter is a wrapper around an object that allows it to do physics. And it was developed that way because each individual supported physics engine, Canon, OEMO, Energy, and Ammo, each have their different ways of doing physics. So what BabylonJS did is said, okay, we need to get the ability to generalize everything here. And so they created what they call physics imposters. And by using these physics imposters, we're able to apply physics to each of these individual objects without regard to whether we're using Ammo or Canon or Energy or whatever. Now I'm using Ammo in this case because it's the most powerful one, as you'll see here in just a second. So the idea here is it's like a wrapper around the object. For example, let's say you've got a haptic device that you put a glove on your hand, and that allows you to control things on the screen. Now, without that glove, you can move your hand all you want, and nothing's going to happen to the screen. But as soon as you put that haptic glove on, then you'll be able to control things on the screen. Now, if somebody else wants to be able to do that, they don't have to have their own glove. You can just give them theirs, and theirs works fine too. That glove basically is a physics imposter in this particular case, or is the same thing as a physics imposter. It's a wrapper around an object that allows us to be able to do physics on that particular object. So now I can take any object anywhere. I can take my Blender objects, I can take my tree, my house, my track, all the cars, the wheels on the car, the wheels on the bus go around and around. Anyway, we can do all of that, and we can put physics imposters around it, and the world will interact with those physics imposters, and with those physics imposters tied to the and with those physics imposters tied to the actual physical objects, it will give the appearance of that object having physics. So that's what these imposters are for. There's a bunch of different ones. I'm not going to go over them at all, but there's a bunch of different ones that will do different things based upon what type of meshes that you have. What we're going to be worried about here, or what we're going to work with, is what's called a collider mesh. And a collider mesh is an invisible mesh that has the physics involved with it that wraps itself around the object, and then everything will interact with those collider meshes. It's real simple to use. So let's go back to our code, and we're going to first of all create a physics imposter on our ground. Now this is just the ground is a box object, basically, if you think of it that way. So the physics imposter, to create a physics imposter, we're going to create a new physics imposter. We're going to say, hey, what are you applying it to? I'm going to apply it to the ground. All right, what type of physics imposter? Well, this is going to be a box imposter, and it's going to create a box. Then I'm going to give it some options, in this case, mass, friction, and restitution. And there's about 7 or 8 different options. These are the ones we're going to be kind of worried about with right now. I may go over these a little bit later on. I hadn't decided yet. And then we pass to a scene. Mass of 0 is a specialized number that you're supposed to use for any kind of ground type objects. Friction is obviously friction. The higher the number, the more friction it has. And that's going to come in very handy. And we'll go through these a little bit later on later. Restitution, that's a pretty fun one. I'll show you that one here shortly. But this basically now says, okay, my ground, which is located right here, now has a physics imposter wrapped around it. And this physics imposter says, okay, now if something collides with me, I'm going to act like I'm a box, and I'm going to apply my friction, I'm going to apply restitution to it, I'm going to apply a whole bunch of different things. Okay, that gets the ground. What about our skull? Well, the skull is loaded in a special routine called import mesh. And this import mesh basically imports a mesh from, in this case, from the models that I have here. And then it calls, on success, it calls a particular function. And it will pass to me all the different meshes that are available with the skull. Now, in our particular case, we're going to only have, we really only have one mesh here. And this mesh is the skull mesh itself. All right, so we do some scaling on the mesh to make sure it scales correctly. What if we don't do the mesh, the scaling? Let me show you something pretty fun. Let's Control S that. Let's go over to our Fun with JavaScript. Let's F5 it. And our skull is so gigantic, enormous, that it completely is encapsulated our entire screen here. So that's why we do the scaling, so we can get it the size that we need. Because you don't know the size of these models that you may get from open source, so you may have to scale them. Then we position set, we position it at 0, 0, 0, no big deal there. Okay, so now we add the collider meshes. And these collider meshes are going to, it's extremely important here. There's a couple of them that are very important. We're going to be building 2 of them, a sphere and a box. And I'll show you why here in just a second. The idea here is that we're going to create a sphere we're going to create a sphere that's going to be representing the head of the skull. We're going to position it in a certain position, and we're going to actually make it invisible. Our collider is visible as false, and we're going to set it to invisible, and that's going to be very important. So this sphere represents one piece of the skull itself, and then we position it based upon the position we have set for the skull initially. We're going to also create a box, and that's going to be for the skull of the mouth, the mandible, I think it's called, the mouth part of the jaw. I can't get the words out. That's going to be that's going to represent the jaw. And so we're going to position the box, and we're going to also make it invisible. Now, before we do that, let me show you why we're doing that. I'm going to set this to true, and then let's rerun our code. Now see, notice how you have the circle which is enveloping the skull part of the skull, the head part of the skull, and the box which is enveloping the jaw. Let me get that back on the screen. So that's the reason that we got the collider. So we've built in 2 different collider meshes to conform as best we can to the skull. The idea is you want to be able to have as few collider meshes as possible, because obviously the fewer collider meshes, the faster your engine is going to run. If we did a collider mesh with each individual small, tiny little piece of the skull, yeah, it'll be absolutely perfect in its collision, but man, talk about the processing power that's going to be needed to run that. And, you know, for right now, I'm not going to worry about that. I just want to have something very simple. So we have created 2 collider meshes. Let's do that again. All right, there we go. So we've created 2 collider meshes. Hey, it almost stuck. Okay, actually, I think it has stuck. 2 collider meshes to best represent the skull itself. It's not perfect, but it gets us very close to, you know, for government purposes, to get the collisions working correctly with the skull. So let's turn that back to false. And now we got our 2 meshes built, the box and the sphere. Let's create our colliders. The idea here now is we first of all create a root. And this physics root is that basically this is going to be a root mesh that is going to have as its children the collider meshes. So we're going to add in the root of the mesh itself, the skull mesh. Then we're going to add in our new box collider, and we're going to add in the sphere collider. And then we're going to position the physics root a little bit higher. We're going to position the physics root just a little bit higher up. Okay, let's enable the physics. And we, just like we did with the ground up here, we're going to enable the physics down here on the box collector, the sphere collector, and the physics collector. But I want to show you something that's very important. The box collider, collider, it's going to have a box imposter. It's going to have a mass of 0, no big deal. The physics imposter is going to do a sphere imposter, and it's going to also have a mass of 0. The important one here is going to be the physics imposter. And the physics imposter is going to have a no imposter. It's going to have a no imposter. And the physics root here, though, is going to have a no imposter relationship. It's not a box, it's not a sphere, it's going to be a no imposter. And that's no imposter is specifically meant for any type of parent, or in this case, root imposter that would contain different children. And it actually has a mass of 3 showing that, hey, okay, our particular imposter has a mass of 3. And remember, this imposter wraps the skull, so now we're saying that this skull has a mass of 3. So we're not giving masses to the skull, we're giving masses to the physics imposter. And the physics imposter is that one single, or the root is that one single collider mesh that contains all the different collider meshes and the meshes for the skull, and gives it some sort of weight. And then we turn it all around to make sure it all matches up with the skull itself. And so that's really what all this part is, and what all this part is just to be able to make sure everything is positioned correctly and perfectly within the skull itself. So for instance, let's just play around with this and see what it does. Don't do the physical position there. Let's see what happens. I tell you what, let's actually put the let's make it true again so we can see what's going on. All right, so there's that. So that looks pretty good. Notice that it immediately starts off in the middle there. So although it looks pretty good, it starts off in the middle. And so that's what this position is all about. Is this, what's our starting point for the skull? And that's why we get the 3 there. So if we made this 1, it's a short little drop. All right, so that's what that does. What about the rotations? What if we didn't have the rotations? What would that do? Well, let's find out. Well, I can't see a difference, can you? So I'm not sure exactly why we're doing the rotations, but hey, there he is. That's the way it is. So we're rotating the physics root. That should rotate everything around. I didn't notice a difference, but there we are. Anyway, so, but that completes the loading of the skull. So the important thing with the skull here is that we've got the colliders, the 2 colliders, the sphere collider and the box collider, that colors, that gives us the area to collide with for all the other objects that best represents as close as we can to the skull. Again, it's not perfect, but we're not looking for absolute perfection here. And then we're creating the physics root, which contains not only the skull, but contains the collider meshes. And then we define all of those here, with the physics root having the mass of 3. And then all I do is just run it. This is what happens. This is the magic right here. JavaScript has an animation frame timing system built into it, which runs about 60 frames per second. And this runs this render loop as fast as it possibly can, as fast as 60 frames per second if it can. And we just tell it to render the scene. And so 60 times a second, we render the scene. And that's why we end up getting this. Works like a champ. So, a couple things I want to talk about before we finish off the video here is let's go back to the ground inspector. Notice it has a mass, a friction, and a restitution. Let's play with friction and restitution a little bit and see what can be done with that. All right, so friction is 0.5. What happens if we put friction to 1? Well, I didn't see much of a difference, did you? All right, well, how about friction of 10? So remember, the higher friction, yeah, see, it isn't moving as much now. So the higher the friction, the more it bitterly resists trying to move. So if we put the friction down to 0, should be no friction. Zoom, boink, and it moves off. So that's cool. So now we know that we can set friction on the ground. So, you know, if we can also set friction on, let's think about this for a second. We set friction on our tires, for example, on our car. The tires may exhibit a certain amount of friction. The track will exert a certain amount of friction, but the tires won't have as much friction on it. But the top of the car, you know, in case the car flips over, it might have a lot of friction on it. So if the car flips over, it may slide a little bit, but it's going to come to a quicker stop. So the friction is going to be very good for us to use. I'll put it back to 0.5. I think it was at 0.5 originally. Where was it originally? Yeah, 0.5. Okay. So the friction we're going to be able to use in both the track and on the wheels and on the cars and everything to be able to find out, you know, hey, what's going to run down the track well and what's not going to. Restitution. And what the heck is restitution? Well, let's put a restitution of, let's start, we got 0.7, so let's put it to 0. See what happens. Doing F5. I didn't see much of a change, did you? Yeah, all right. Let's put a restitution of 1. Ah, there was a change there. Notice this time it bounced a little bit, so maybe restitution is some sort of bouncy factor. Yeah, notice it bounced a little bit. Yeah, let's go back to 0. Let's go back to 0. It was 0.7 originally. Let's go back to 0. Yeah, looks like restitution is a bouncy value. So let's put a restitution of 5. Let's see what happens. Boing, boing, boing. That's great. Okay, so restitution is the bounciness of our, I like that, is the bounciness of our fabric, of our mesh here. So, you know, obviously we're not going to have a lot of bounciness on the track, you know, but our tires are going to have a little bit of bounciness. You know, the car makes a jump. You know, let's make sure a little further down the road we have jumps within our we have jumps, and so you know when it lands that jump, it's going to have to bounce somewhere. So that would be cool. Let's knock it up to what happens. Let's put it at 10. Let's see what happens. Boom! There it goes. Okay, yeah, I'm gonna have a lot of fun with restitution. This is gonna be great. I wonder if you can have a negative restitution. Let's find out. All right, how about let's have a -5. Absolutely 0 bounce. Of course, I got a feeling once you get really below 0, it just kind of makes it's really nothing to it. It makes it 0. So I don't think having a negative number is going to make a difference there. So this is really cool. So we know that in restitution is our bounciness, and that friction is obviously friction. So this is great. So we now have exactly the concept of what we want to do here. We have a mesh. Let's turn off the collider mesh. Let's turn that back to false. So we know that we have a model that we can load in. So any kind of car model we can load in now using the import mesh. We know we have a ground that we can slope. And we know that we can have this mesh interact with this ground. So if it's slopey enough and there's enough friction, or there's not enough friction, then our little model is just going to slide or roll or do whatever on the ground. And that proves that gravity works. So we actually now have the basics of what we're looking for here. We can get an object that is affected by gravity, that is also affected by friction and by bounciness, and that we can have it collide. So if we had 2 or 3 different skulls in there, they should collide with each other. Then that basically completes now our proof of concept for our physics. If you like this video, please click on the like button below, subscribe to this channel, or leave a comment. I'd love to hear from you. And thank you so very much for watching. This is the Virtuoid, aka Mike Smith. We'll see you later.